Tailing out is a wiring technique employed in electrical systems to minimize the current flowing through a receptacle, often abbreviated as REC, and to ensure proper circuit balancing. The process involves specifically tying all the neutral wires together within the electrical box. Crucially, only the hot wires are then connected directly to the receptacle. The primary purpose of tailing out is to distribute the current from the branch circuit evenly among all the receptacles connected to that circuit. Typically, when a receptacle is in use, the current flows from the hot wire through the receptacle itself and then returns to the electrical panel via the neutral wire. However, when the neutrals are tied together using the tailing out method, the current is afforded an alternative path. It can choose the path of least resistance, which may effectively bypass some of the other receptacles within the circuit. There are several benefits associated with this approach. Firstly, tailing out aids in circuit balancing. By tying the neutrals, an equal amount of current will flow through each receptacle, and this prevents any particular receptacle from being overloaded. Secondly, this technique reduces the receptacle load. By reducing the current flow passing through each individual receptacle, tailing out can extend the lifespan of the receptacle and prevent overheating. Thirdly, tailing out ensures proper voltage distribution. With this wiring method, all receptacles will receive the same voltage. This uniformity ensures the proper operation of any appliances and devices that are connected to those receptacles. Some additional details to keep in mind. It is important to strictly adhere to all relevant electrical codes, such as those outlined in the National Electrical Code, or NEC. In this case, we will use the 2008 edition of the NEC, and you should consult with a qualified electrician when performing any type of electrical work. Tailing out should only be implemented for receptacles that are part of the same branch circuit. Attempting to apply it across different circuits can create dangerous situations. Remember to always prioritize safety and consult with a qualified electrician when dealing with electrical installations or modifications. Branch circuit wiring involves numerous considerations as outlined in the National Electrical Code, or NEC. Proper grounding is a fundamental aspect of electrical safety. Grounding ensures that metallic parts of an electrical system that aren't supposed to carry current won't become energized in the event of a fault. Grounding provides a low impedance path for fault current to return to the source, tripping a circuit breaker or fuse and de-energizing the circuit. The grounding electrode conductor connects the system's grounded conductor, typically the neutral, to a grounding electrode. This electrode can be a ground rod, a metallic water pipe, or a concrete-encased electrode. The size of the grounding electrode conductor is determined by NEC Table 250.66, based on the size of the service entrance conductors. Equipment grounding conductors, or EGs, provide a ground fault current path for non-current carrying metal parts of equipment. These conductors can be wires, metallic raceways, or cable armor. Their size is determined by NEC Table 250.122, based on the overcurrent protective device protecting the circuit. Bonding ensures electrical continuity and conductivity. Bonding jumpers connect metallic parts together to create a low impedance path for fault current. These jumpers are used to bond metallic enclosures, raceways, and other non-current carrying metal parts. Sizing of bonding jumpers is also covered in NEC Table 250.122. Overcurrent protection is vital for preventing overloads and short circuits. Circuit breakers and fuses are the most common overcurrent protective devices. They are designed to interrupt the flow of current when it exceeds a predetermined value. The selection of the appropriate overcurrent device must be based on the ampacity of the conductors it protects. NEC Section 240.4 details the requirements for overcurrent protection of conductors. Conductors must be sized appropriately for the load they will carry. The ampacity of a conductor, its current carrying capacity, is determined by its size, insulation type, and installation conditions. NEC Table 310.16 provides ampacity ratings for various conductors based on these factors. Correction factors and adjustment factors must be applied when conductors are used in environments with high ambient temperatures or when multiple current-carrying conductors are bundled together. Voltage drop is a reduction in voltage that occurs as electrical current flows through a conductor. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to no more than 3% in branch circuits and 5% in feeders. Voltage drop can be calculated using formulas that take into account the conductor length, current, and resistance. Wiring methods refer to the physical means of installing electrical conductors. Common wiring methods include rigid metal conduit, electrical metallic tubing, or flexible metal conduit, armored cable, and non-metallic sheath cable, or NM cable. Each wiring method has specific applications and installation requirements outlined in the NEC. Proper support and securement of wiring is essential for safety and reliability. Conductors and cables must be supported and secured in accordance with the NEC requirement. Support intervals vary depending on the wiring method and conductor size. Terminations and splices must be made in a safe and reliable manner. Connections must be mechanically sound and provide good electrical contact. Wire connectors, such as wire nuts, crimp connectors, and terminal blocks, are used to join conductors. All terminations and splices must be made inside approved enclosures. Receptacle spacing in residential dwellings is governed by NEC Section 210.52. Receptacles must be installed so that no point along the wall line is more than 6 feet from a receptacle. This ensures that occupants can easily access power without using extension cords. Ground fault circuit interrupters, or GFCIs, are life-saving devices that protect against electrical shock. GFCIs detect ground faults, which occur when current leaks from a circuit to ground. When a ground fault is detected, the GFCI quickly interrupts the power supply, preventing a potentially fatal shock. GFCIs are required in bathrooms, kitchens, garages, and outdoor locations. Arc fault circuit interrupters, or RFCIs, protect against fires caused by arcing faults. Arcing faults occur when electricity jumps between conductors, creating heat that can ignite nearby materials. RFCIs detect arcing faults and interrupt the power supply, preventing a fire. RFCIs are required in many locations throughout the home, particularly in bedrooms. Electrical boxes are enclosures used to house electrical connections and protect them from damage. Boxes must be sized appropriately for the number and size of conductors they contain. NEC Article 314 provides requirements for box fill calculations. Different types of boxes are available for various applications, including surface mount boxes, flush mount boxes, and weatherproof boxes. Cable entry methods into boxes must comply with NEC requirements. Cables must be secured to boxes using cable clamps or connectors. Unused openings in boxes must be closed with appropriate closures. Understanding and applying these branch circuit wiring principles is essential for safe and compliant electrical installations. Always refer to the latest edition of the NEC and consult with a qualified electrician when performing electrical work. Additionally, safety is important when working with electricity. Firstly, always turn off the power at the circuit breaker before working on any electrical circuit. Secondly, use insulated tools to prevent electrical shock. Thirdly, test circuits with a voltage tester to ensure they are de-energized before working on them. Fourthly, wear appropriate personal protective equipment, such as safety glasses and gloves. Fifthly, never work on electrical circuits in wet or damp conditions. Sixthly, follow all safety procedures and guidelines outlined in the NEC. Seventhly, if you are unsure about any aspect of electrical work, consult with a qualified electrician. Eighthly, ensure proper ventilation when working in enclosed spaces. Ninthly, keep your work area clean and free of clutter. Tenthly, double-check all connections before energizing a circuit. Beyond the specific technique of tailing out, there are other essential aspects of electrical wiring to consider. Understanding these concepts will contribute to a safer and more efficient electrical system. First, consider load calculations. Determining the correct size of conductors and overcurrent protection requires accurate load calculations. This involves calculating the total amperage of all devices and appliances that will be connected to a circuit. The NEC provides detailed guidelines for calculating various types of loads, including general lighting loads, appliance loads, and motor loads. Second, think about conductor selection. Choosing the right type and size of conductor is critical for safety and performance. Conductors are available in various materials, including copper and aluminum. Copper is generally preferred for its higher conductivity and lower resistance. Conductor size is determined by its ampacity, which is the amount of current it can safely carry. NEC Table 310.16 provides ampacity ratings for different types of conductors based on their size and insulation. Third, think about conduit fill. When running conductors through conduit, it is essential to comply with conduit fill requirements. Conduit fill refers to the percentage of the conduit's cross-sectional area that is occupied by conductors. The NEC limits conduit fill to prevent overheating and ensure ease of installation. Conduit fill calculations are based on the size and number of conductors in the conduit. Fourth, think about grounding and bonding. Proper grounding and bonding are essential for electrical safety. Grounding provides a path for fault current to return to the source, tripping a circuit breaker or fuse and energizing the circuit. Bonding ensures that all metallic parts of an electrical system are electrically connected, creating a low impedance path for fault current. The NEC provides detailed requirements for grounding and bonding, including the sizing of grounding and bonding conductors. Fifth, consider surge protection. Surge protective devices, or SPDs, protect electrical equipment from voltage surges caused by lightning strikes or other transient events. SPD diverts surge current to ground, preventing it from damaging sensitive electronic equipment. SPD are available in various types and sizes, and they should be installed at the service entrance and at branch circuits. Sixth, think about electrical inspections. Electrical inspections are conducted by qualified inspectors to ensure that electrical installations comply with the NEC and other applicable codes. Inspections are typically required for new construction, renovations, and repairs. Passing an electrical inspection is essential for obtaining a certificate of occupancy and ensuring the safety of the electrical system. Seventh, think about energy efficiency. Energy efficient electrical systems can save money on electricity bills and reduce environmental impact. Energy efficient lighting, appliances, and HVAC systems can significantly reduce energy consumption. The NEC includes provisions for energy efficiency, such as requirements for occupancy sensors and daylighting controls. Eighth, think about future expansion. When designing an electrical system, it is important to consider future expansion needs. Adding spare capacity to the electrical panel and installing extra conduit can make it easier to add new circuits in the future. Planning for future expansion can save time and money in the long run. Ninth, consider preventative maintenance. Regular preventative maintenance can help to keep an electrical system operating safely and efficiently. Preventative maintenance tasks include inspecting wiring, tightening connections, testing circuit breakers, and cleaning electrical equipment. Following a preventative maintenance schedule can help to identify and correct potential problems before they cause a failure. 10th, consider documentation. Maintaining accurate documentation of the electrical system is essential for troubleshooting and maintenance. Documentation should include electrical drawings, panel schedules, and equipment specifications. Keeping the documentation up to date can save time and money when repairs or modifications are needed. These additional considerations are crucial for ensuring the safety, efficiency, and reliability of electrical systems. Always consult with a qualified electrician and refer to the latest edition of the NEC when designing, installing, or maintaining electrical systems. Remember that electrical work can be dangerous, and it should only be performed by qualified individuals. When working with electrical systems, it is crucial to understand the different types of circuits and their specific applications. Branch circuits, feeder circuits, and service circuits each play a distinct role in the distribution of electrical power. Firstly, branch circuits are the circuits that supply power to individual outlets, lights, and appliances. They are typically protected by 15 amp or 20 amp circuit breakers. Branch circuits are designed to serve a specific load or a group of loads within a defined area. The NEC provides detailed requirements for the number and spacing of receptacles on branch circuits, as well as the types of loads that can be connected to them. Secondly, feeder circuits are the circuits that carry power from the service equipment to sub-panels or other distribution points. They are typically larger than branch circuits and are protected by higher ampacity circuit breakers. Feeder circuits are designed to supply power to multiple branch circuits or to large loads, such as HVAC systems or industrial machinery. The NEC provides requirements for the sizing of feeder conductors and overcurrent protection based on the calculated load. Thirdly, service circuits are the circuits that connect the utility company's power grid to the customer's electrical system. They are the largest circuits in the electrical system and are protected by the main circuit breaker or fuse. Service circuits are designed to deliver the total electrical power required by the building or facility. The NEC provides detailed requirements for the service entrance, including the size of the service conductors, the grounding system, and the overcurrent protection. Understanding the differences between these types of circuits is essential for designing and installing safe and efficient electrical systems. Each type of circuit has its own specific requirements and limitations, as outlined in the NEC. In addition to the types of circuits, it is also important to understand the different types of wiring methods. Wiring methods refer to the physical means of installing electrical conductors. There are many different wiring methods available, each with its own advantages and disadvantages. Some of the most common wiring methods include: firstly, rigid metal conduit, or RMC, is a heavy walled tubing that provides excellent protection for conductors. RMC is typically used in commercial and industrial applications where high strength and durability are required. RMC is installed using threaded fittings and is typically grounded by connecting it to the grounding electrode system. Secondly, electrical metallic tubing, or EMT, is a thin-walled tubing that is lighter and easier to install than RMC. EMT is typically used in residential and commercial applications where less protection is required. EMT is installed using compression fittings or set screw fittings and is typically grounded by connecting it to the metal enclosures. Thirdly, flexible metal conduit, or FMC, is a flexible tubing that allows for movement and vibration. FMC is typically used to connect motors and other equipment that may move or vibrate. FMC is installed using connectors and is typically grounded by connecting it to the grounding electrode system. Fourthly, armored cable, or AC, is a cable that consists of conductors wrapped in a flexible metal armor. AC cable is typically used in residential and commercial applications where protection from physical damage is required. AC cable is installed using connectors and is typically grounded by connecting the armor to the grounding electrode system. Fifthly, non-metallic sheath cable, or NM, is a cable that consists of conductors wrapped in a non-metallic sheathing. NM cable is typically used in residential applications where protection from physical damage is not required. NM cable is installed using staples or cable ties and is typically grounded by connecting the grounding conductor to the grounding electrode system. Choosing the right wiring method for a particular application depends on a variety of factors, including the environment, the type of load, and the budget. It is important to consult with a qualified electrician to determine the best wiring method for a specific project. In conclusion, tailing out is a useful technique, but it should be implemented with a full understanding of electrical principles and in accordance with the NEC and with the guidance of a qualified electrician.